Let's get a little more familiar with antiderivatives by practicing them on functions which are just a power of x. Now if you recall, we have a nice rule that tells us how to differentiate a power of x. It's known as the power rule. The derivative of x to the n is equal to n x to the n minus 1. Now for integrals, or antiderivatives, we need to do that backwards. When we do an integral, what we're doing is we're asking the question, what is a function capital F of x, such that if I took the derivative of that capital F, I would result in the function I see here in the integral. So the integral of x to the n dx is going to be whatever function differentiates into the function x to the n. Now I'm claiming that the same power rule that says this is also the power rule that tells us how to integrate x to the n. The integral, or antiderivative of x to the n dx, is going to be x to the n plus 1 divided by n plus 1 plus c. Now if you saw the last video, you remember and you know what the plus c is, the constant of integration, and that appears on all indefinite integrals or antiderivatives because when we take the derivative of the plus c, it goes to 0. So we don't know what the plus c was. Okay, now if you don't believe me that I have this fact on the board, here's a nice proof. Get used to this type of proof because every time you do an integral, you can just take the derivative and you should get for the derivative what you started with in the integral. It's a proof or a check that you have the right answer. Okay, so if I think the integral of x to the n dx is equal to this, then if I take the derivative of this, I should get x to the n. That's what I've got in my proof right here. The d dx of x to the n plus 1 divided by n plus 1 plus a constant is equal to, well, according to the power rule here, what happens is the power comes down and it multiplies anything in front. So see, the power was n plus 1, and it comes down and it multiplies the 1 over n plus 1 that I was dividing by. That's great because those cancel, and this term right here cancels out into 1. And then my power goes down by 1. So if my power is x to the n plus 1, I have to minus 1 to that. That's the same minus 1 that you see here. And n plus 1 minus 1 is just n. Now x to the n is the thing that I was asked to integrate. So if I find a function right here, where when I take the derivative I get x to the n, then this function right here is the antiderivative of x to the n. Awesome. Notice the plus c has a derivative 0, so that's why the plus c disappeared, and that's why the plus c appears every time we take an integral, which is just doing derivatives backwards. Okay, are you ready for some practice by yourself? Alright, so I've got some integrals lined up right here, also known as antiderivatives. Now what I'm asking for you is, what is the function such that if I took the derivative of it, the derivative of the function is 3x squared? Okay, and that question is posed mathematically by writing what is the integral of 3x squared dx. Now you can use this power rule right here if you like, but oftentimes it just comes down to guessing. Does that sound familiar? The derivative of my function is 3x squared. What was my original function? X cubed, right? That's right. Well, really, x cubed plus c. And how do I know that for sure? I can check, and keep this in mind because you can check too. Every single time you do an integral, you can always perform a check on the side by taking the d dx, the derivative of what you guessed. Of course, every time the plus c goes to 0, and the derivative of x cubed is 3x squared. With 3x squared, that's what I was asked to integrate right there. It perfectly matches, so I know I got the answer, okay? So that's how you should do it. Check your answer every time. That's the right answer. Alright, so now for another one, I'm asking you to integrate x to the 4th. I'm asking you to find a function for me such that if I took the derivative of that function, I would get x to the 4th. Now notice that this directly matches the statement I have right here where the letter n is equal to the number 4. So if you like, you can plug in the number 4 and get the answer right here. Alright? Well, but I kind of want you to do it in your head because that's usually how people end up doing it, right? X to the 4. X to the 4. Okay, so where did x to the 4 come from? It must have come from x to the 5, right? Because when I take the derivative of x to the 5, then it goes down by 1 to give me x to the 4. But if I took the derivative of x to the 5, what would happen? I would get 5x to the 4, right? But I don't have 5x to the 4, I just have 1x to the 4. So I guess I have to divide that by 5 so that the 5 will cancel out. And that's exactly what this equation's trying to tell me. If you integrate x to the n, you get x to the n plus 1 because it's 1 higher, but you have to divide by the n plus 1, just like how I had to divide by the 5 because the 5 will cancel each other when I take the derivative, right? And don't forget the plus c. Every time you're taking an indefinite integral, don't forget about the plus c, because truly the answer here is the family of functions which make up all vertical translations of that polynomial. Alright, and once again, I'm going to just do my check. What's the d dx of x to the 5 over 5? Well, because the plus c goes away every time, you don't even really need to include the plus c in your check if you don't want. Everybody knows that's going to go to 0. But anyway, this derivative here would be 5x to the 4 over 5, and that cancels, so I get x to the 4. And that's what I was asked to integrate. Great. So now I can check my work every time, which makes me feel really good and confident about my answer here. Alright, this final one is a little bit harder. I put a 4 in front of this. It's 4x to the 7. Alright, so what is going to happen here? I need a function that when I take its derivative, I end up getting x to the 7, right? Now where would an x to the 7 come from? X to the 8, exactly. It would have to come down by 1, so I must have started with something that was x to the 8. Right, but if I take the derivative of x to the 8, I get 8x to the 7, and I actually only have 4x to the 7s. So if I divide that by 2, that's what's going to make me end up with a 4x to the 7. And don't forget the plus c, of course. So on my check right here, I have x to the 8 over 2. I'm not going to derive the plus c, because that's just going to go to 0. But from my check here, I can see that the 8 comes down, and it gets divided by 2, and so that's 4x to the 7. Bingo! That's exactly the answer that I got. Alright, starting to get used to this now? Alright, great. So it's going to get a little more complicated than that, but hopefully those simple examples have got you in the mood to take some more antiderivatives. Now one thing I want to say before we get into the harder examples is that integrals follow some of the same rules that they share the same rules as derivative. Same rules as the derivatives. And that's because integrals are intimately related to derivatives. They are derivatives backwards. Alright, they share the same rules as derivatives, which is to say one of the rules that we had for derivatives was if we had a little constant multiplied by a function, that was equal to taking the constant outside and then taking the derivative of the function. This was called the constant multiple rule for derivatives. Once again, if you take the derivative of a constant multiple times a function, that's the same thing as taking the constant multiple outside of the derivative and then just taking the derivative of the function. We were pulling constants outside when we were taking derivatives all the time. Well, guess what? It's the same thing for an integral. If I take an integral and I have a little constant times a function, that's the same thing as pulling the constant out front and then just taking the integral just like that. Okay? So if I have a constant c multiplying that little f of x that's known as the integrand, I can pull the constant c outside and then I can just take care of the integral and then the plus c, this is not the plus c, this is a constant multiple, will just be sitting on the outside. Okay, let me illustrate this with this function right here that we just did. We had 4x to the 7. Now, I want to compare this with the integral right above it. So when I asked you to integrate x to the 4, you knew that it was going to be x to the 5, because 5 is 1 higher than 4, and then you divide by the same number that you raised the x to. If you want to use that rule all the time, then you could use it on this by combining it with the constant multiple rule. You see, there's a 4 inside this integral, right? But that's a constant multiple, so really if I want, that's the same thing as pulling the 4 outside the integral. Did you see what happened there? You can do that as much as you want. As long as it's just a constant multiplier, the number 4 here, you can take it and put it outside the integral. Same thing we were doing with derivatives. Because that might make it a little easier for me to figure out, you see, because the 4 is just sitting out there waiting for me, and if I have an x to the 7, very similar to the x to the 4, I know that it's going to be 1 higher and divided exactly by what I raised to the power 2. So if you don't like the guessing method that we used at first, you can actually use the constant multiple rule method to just isolate the single power of x that you need to integrate, and then you'll have x to the 8 over 8. You see those 8's match? And then the 4 is just sitting on the outside waiting for me, and then those cancel out to be 1/2 x to the 8. And of course, in the final analysis, do not forget the plus c. Same thing we could have done up here, so I'll just show you that one more time. Here we have the integral of 3x squared dx. Well, that's the same thing as saying 3 integral x squared dx. You can just pull the 3 right outside. And now to prove to you that you're going to get the same answer, you see I can take the 3 outside, and now when I have an x to the 2 to deal with, that's going to be x to the 3 over 3. That 3 matches with that 3 so that they would cancel out, and the 3 that I pulled outside is just waiting for me right there, and so it's still x to the 3 plus c. This is a very handy rule. You might want to use this rule all the time, so keep that in mind. And then we have one other rule from derivatives, which was known as the sum and difference rule. That was the fact that the ddx of two functions, f of x plus or minus g of x, either it's plus or minus, whichever one it is equal to just taking the derivative of f of x and then plus or minusing the derivative of g of x. Okay, this was called the sum/difference rule. And we were using this rule as well all the time because a lot of times we have polynomials, and the polynomials are all combinations of different powers of x, and then they all have their own constant multiple. So you see how both of these rules are going to come really in handy when we're doing the integrals as well. So this was the derivative rule, and the corresponding rule is the fact that if you wish to integrate little f plus or minus little g dx, then you can simply integrate little f dx and then plus or minus the separate integral of little g dx. Okay, so just as I broke the sum or difference of derivatives apart, likewise I can break the sum or difference of two integrals apart. Okay, so let's see that one. Like, for instance, maybe if we combine some of these. For instance, maybe we have the integral of 3x squared plus x to the 4 dx. Now, we actually just did both of these on this board, but now I'm asking you to integrate the sum. How are you supposed to do that? It's as easy as just integrating each individual term and then putting those together in the sum. So according to the sum and difference rule, that will be 3x squared dx plus integral x4 dx. And then, if you like, you can even take out the 3 and do it like this, and then the x4 dx. And then you can see how it would just come down to applying the rule that the x squared goes to x3 over 3, and the x4 goes to x5 over 5, and then don't forget the plus c. Okay? You might want to simplify that by canceling the 3's right there, so that the answer would be x to the 3rd plus x5 over 5 plus c. Alright, now these constant multiple and sum and difference rules are extremely handy, so please know about them and make use of them. Are you guys ready for some harder examples now? Let's do some even more challenging examples now that we have those rules. In fact, now that we have those rules, we can pretty much integrate any polynomial, which is exciting because in business applications, polynomials are the most common functional forms. So now, if we have a derivative, like let's say we have a marginal quantity, we could try to get an idea of what the total quantity is in its functional form by anti-deriving it, taking the integral of it. Okay, so here's some harder examples. What about 2 plus x squared dx? Can you integrate that? What about 5 minus the square root of x dx? How about that one? Keep in mind that every time you guess an answer or derive an answer, however you integrate your answer, you can always check your answer. Keep in mind that you can always check your answer by taking derivatives, and you definitely should, because it'll tell you if you got it right, and if it's not right, it'll probably lead you with hints as to where you might have gone wrong. Alright, so we're going to have 2 more. This one right here, and this integral right here. In each of these cases, you have powers of x. Sometimes you might want to try simplifying some of this stuff before you attempt to integrate. Okay, I would love to hear that you guys tried all of these on the board by yourself before you looked at the answers. So now's your chance. Pause the video and try some of these out. Okay, so how far did you get? Hopefully, since we just went over discussion of polynomials, you were able to get this one right here. Was this term maybe actually easier than the 2 term? Because you know that the x squared term is going to go to x3 over 3, right? But what happened to the 2? What kind of function has a derivative just equal to 2? 2x, exactly, 2x. That's almost like a trick question sometimes because people get confused about the fact that constants go to 0, so that's why I have to put the plus c because those will all go to 0. But linear functions go to a constant. So if you ever see a constant inside your integrands right here, then it's going to move into the corresponding linear functional form. Alright, did you get that one? Sweet. Now this one's a little harder. It's got that constant there, and then it's got minus square root of x. I didn't even go over fractional powers with you yet. I was kind of pushing you to see that if you could do on your own fractional powers, and this one's going to be negative powers. Okay, the same rules apply, but you most likely would want to rewrite the square root of x as x to the 1/2. That way you can see how you're going to use the power rule where here the n is equal to 1/2. Yes, it works on fractions. Yes, it works on negative numbers as well. Okay, so what's going to happen with this one? Well, the 5 simply turns into 5x, right? And the minus sign, that's a constant multiple, so the minus sign just carries through. And now the challenge is, what is the integral of x to the 1/2? Let's see, x to the 1/2 came from something where we had 1/2 plus 1, right? It must have come from 1 power higher, exactly 1 higher. Now what's 1/2 plus 1? That's equal to 3 over 2, right? So it must have come from x is equal to 3 over 2. But when I take the derivative of x to the 3 over 2, the 3 over 2 comes down. And I don't see any 3 over 2 right here, so that means I'm going to have to multiply by 2 over 3 in order to cancel out the 3 over 2 for it to come down. That was kind of a tricky one. Did you guys get that on your own? That would be awesome. So also I just want you to know that maybe you wrote it like this, x to the 3 over 2 divided by 3 over 2. That's really where it comes from, because notice you're always dividing by the same exact number that you raised the power to. So here it turned out to be a 3 over 2 because that's 1/2 plus 1. So we had to divide by 3 over 2, and that's the same as multiplying by 2 over 3. Generally, you're going to want to answer in this form right here, as opposed to this. This is kind of a natural to be dividing by a fraction. So you want to simplify it and put it like that. Oh yeah, don't forget about checking your work. Now if you're not sure in any way that you didn't get the answer right, don't forget that you can always just do a quick check by taking that derivative. The derivative of 5x is 5. The derivative of this over here is, well, the 2/3 multiple stays there. The 3/2 comes down like that. And then I get x to the 3/2 minus 1. So you see, this 2/3 cancels with that 3/2, and x to the 3/2 minus 1 is minus x to the 1/2. So I get 5 minus x to the 1/2, and that's what I started with. It's perfect. I really like this part of the class because I can check every single one of my answers and make sure that I got it right. Okay, so here comes another one. Now this is another little sneaky one because I didn't tell you how to do it on a negative power. But I didn't tell you because when I wrote down the power rule, I didn't say that n had to be positive. I didn't say it had to be a whole number. It actually worked on fractions, and it works on negative numbers too. The only thing it doesn't work on is 1 over x. So if you have x to the minus 1, you can't integrate that because when you add 1 to that, you get 0. It kind of gets messed up, and we'll talk about that later. The answer is the logarithm function. But anyway, this is minus 3. So if I add 1 to minus 3, nothing's going to get messed up about that. I'll still get a reasonable answer. Okay, so when I integrate this through, I'm going to get x to the minus 3 plus 1. Keep in mind, you're always adding 1. Just like how I did a half and I added 1. Even though I have a minus 3, I'm just going to add 1. So what's minus 3 plus 1? That's x to the minus 2. But if I take the derivative of that, then the minus 2 comes out in front. So it makes sense that whatever I put up top there, I am likewise going to have to divide off by, so that when I take the derivative, the exponent coming down will cancel with its match right there on the bottom. Okay? So that ends up being the answer. X to the minus 3 integrates into x to the minus 2 divided by minus 2. And if I don't believe myself, then I can always check by taking the d dx, and that's going to be minus 2 times x to the minus 2 minus 1, and that was all over minus 2. Cancels, cancels, and so I get x to the minus 3, and that's what I was asked to integrate. Now, notice that when you're doing these problems, I am challenging you to be able to recognize fractional powers, recognize negative powers. You're going to have to be able to do that before you can even get started with the integral. And this is my hardest one so far. Not only did you have to recognize that this is a fractional power, but you had to divide off by it so that you get an integral, which is just a bunch of terms, x to the something, x to the something. So if this one made you stuck, here's my hint right now, is that I want you to simplify it, okay? Really, this is the integral of x to the 2 divided by x to the 1/3 dx. And really you can see that as x divided by x to the 1/3 plus 2 divided by x to the 1/3 dx. So before I even attempt this integral, I'm going to need to simplify it down. That first term right there is x to the what? And then that second term right there has a 2, and I'm going to write it with the x on top. That's x to the what? Dx. Now once I answer where those question marks are, then it will be easy for me to start enacting the rule, the power rule that I learned. Okay, so practice this right now. This is pre-calculus skill. This first term, x divided by x to the 1/3, what is that? X to the 1, x to the 1 minus 1/3 is x to the 2/3. Alright, so that first one was x to the 2/3. This one right here is 2 divided by x to the 1/3, so what am I going to put there? If I want to put the x on top, which it has to be in order to use the rule, that's x to the minus 1/3. You see when the x was on the bottom here, x to the 1/3, I had to put it with the x on the top before I can use the rule, because the power rule is stated as the integral of x to the n, where the x is on top. Okay, so this has to be x to the n. In this case, n is minus 1/3. In this case, n is 2/3. Okay, now I can enact the rule. What I'm going to do to integrate is I'm going to add the number 1 to each one of these exponents individually. So 2/3 plus 1 is 2/3 plus 3/3, which is 5/3. So the first term is x to the 5/3, and of course I have to divide by that same 5/3 so that they will cancel each other out. Okay, next one, the 2 is just floating out in front, it's just a constant multiple. And then I have, let's see, it was x to the minus 1/3, and I'm going to add 1 to that, so I'm adding 3 over 3. And so what do I get? Is 2 over 3. But don't forget, you got to divide off by that same exact 2 over 3 so that they'll cancel out. And then I have plus c. Okay, I'm almost done with this, but again, I don't really like to answer this with the fractions on the bottom. So what I'm going to do is I'm going to erase this line up here, and I'll just write down the official answer. This is going to be x to the 5/3, and then when I flip the fraction, that's 3/5. This is going to be x to the 2/3, and you see when I flip this fraction, the 3 comes on top, and the 2 cancels with that 2 right there. So really, I just get a 3 right there, and then plus c. Okay, so I pretty much think I did it, but I don't want to get out of here until I check my answer. If anything did go wrong, when I check my answer, I'll kind of be led as to where I went wrong. Okay, so I'm going to check by taking the d dx, and for this one, the 5/3 comes down, and it multiplies the 3/5, and I get x to the 5/3 minus 1. Next one, the 2/3 comes down, and it multiplies the 3, and I get x to the 2/3 minus 1. Okay, so what is that? Cancels, cancels, and 5/3 minus 1 is 2/3. Over here, the 3's cancel, and I get 2x to the minus 1/3. And was that not the thing I was asked to integrate? Oh, well actually it was. Once I simplified this down and rewrote this as powers, you see that's what I got for the powers, and so it does check out. Okay, so you see you're going to need a lot of your previous skills in order to do these integrals.